For this problem, we were first given the initial velocity of an object thrown at a certain angle and the distance that it traveled before it landed. So with this information, we were then asked to find the angle at which the object was initially thrown at. So to do this, I can establish, or at least I can know, my two equations roughly. So my two equations, what I mean by that is x equals whatever the velocity is, cosine theta t. And because I don't know theta, I can't find the horizontal velocity, which is what this represents right here. The t just represents time, and then 300 right here, which would be x. If you didn't know that, is the distance that it travels overall. Because this a value, which is the velocity, is given to us in miles per hour, we had to change that through some basic conversions to find our feet per second value, which I found to be 132, just multiplying 90 by 5,280 to get it out of into feet and out of miles, and then dividing by 3,600, which to get from hours to seconds. So now with all that information, I can plug it into my horizontal velocity equation, which turns out to be 300 equals 132 cosine theta t. And then I would solve for t in this case, because that's the common variable besides theta between these two that's easiest to solve for. So t here equals 300 over 132 cosine theta. Now I can plug that into my vertical velocity, which would be which acts as the parametric. So when combining these two, you make the overall throwing arc that happens, like how it goes up and then comes down from gravity. So that horizontal would be negative 16 t squared plus 132 sine theta t, 132 sine being the vertical velocity of this object, and then plus 3. The plus 3 is the starting height at which the object was thrown. By substituting in this t that we found earlier for t in this equation, we get negative 16 parenthesis 300 over 132 cosine theta, all of that squared, plus 132 sine theta times 300 over 132 cosine theta plus 3. Now, by solving this algebraically or graphing it, you can do it either way, you should get theta equals 16 degrees and 73 degrees. And so we can plug these in and find that only 16 degrees works. So knowing that, I will go with 16 and work with 16. So since we know that 16 works in this problem, you can find that by checking your answer by graphing it, but it's probably going to be the lower one because 73 would almost be straight up, which is not true. Not accurate to the situation. So we can plug this value, now that we know it, back into this original horizontal velocity equation and find our t value, how long it was really in the air for. So 300 equals 132 cosine 16. Do the same thing like you did to solve for t, and you find that t equals about 2.2 seconds. And then by knowing this, you can put in this equation right here, x equals 132 cosine 16t, which will allow you to solve for t again, but now you'll have x, which is, as we know, the distance that it goes. But by putting this back into this original vertical velocity equation right here, that will give us the actual throwing arc curve. This gave us a different curve up here to find these angles. If you looked at where whatever this gives you, this graph, where it intersects with the x-axis, that would be your angles. So it intersects at 16 and 73. But for this one, it gives us the actual throwing arc. So it starts at 0.3 because it was thrown from a starting height of 3, tossed over a distance of around 300 feet and lands at around 300 feet. And if you put this in, you do get to x to be about 300 feet, which confirms our problem, and we know that we did everything right, and our t value and angle was correct. So we can conclude that the throwing angle was about or exactly 16 degrees.